Welcome back to part 3 of angle and orthogonality in an inner product space. At the end of our last video, we were taking our matrix and found a basis for the row space, column space, null space, and null space of A transpose. What I want you to do now is take a second, pause the video, and try to draw a picture for the row space and the column space in 3 dimensions, and do the the row space and the null space, and then the column space and the null space of A transpose. Try and draw a picture here, and then I'll show you my picture using technology here in just a second. All right, so here I have the vector -2, 1, 3. That's the orange vector. And then I've got the blue vector 0, 2, 2. And you can see the XY plane here in gray. I'm going to take that off, and I'm actually going to graph the plane that those two vectors span, that they cover using linear combinations. And so these guys were the row space of the A matrix. Let's graph vector C. You'll see that he's not in that plane. In fact, if we take a look and do what he covers, so his null space, I'll scalar multiples of him, we get a line through the origin, and not just anything about that, but you'll notice that that line through the origin happens to be perpendicular to the plane. So that means anything in the null space is perpendicular to anything in the row space plane. Okay, that's pretty spiffy. Well, what about the other way around? What about the column space of matrix A and the null space of A transpose? So here I've got the column space vectors of -2, 0, -1, and 1, 2, 3 in pink and blue, or sorry, pink and green again. And you can see that they span a plane. And if I create the null space of A transpose vector, again, I'll call him purple here. And if I do his line, you'll see that that line for the null space of A transpose is orthogonal to, or perpendicular to, let's see if I can get this to work here, perpendicular to everything in the plane. Cool. So that kind of sort of makes sense, doesn't it? So if the row space is orthogonal to the null space of the matrix, when we do the transpose of the matrix, that would be the column space would now be the row space, and the null space of A transpose. So that's something very important to note, that the row space of a matrix and the null space of a matrix are always going to be orthogonal subspaces to each other. So let's go back to our paper. Okay, so hopefully you were able to make your own picture here. And how did our row space compare to the null space? Well, if we take -2, 1, -3, and we dot product with the null space vector of -2, -1, 1, aka the Euclidean inner product, we will get 4, -1, -3, which is 0, showing that the two vectors are orthogonal. But what about the other vector in the row space? Let's do him with our null space vector and find out what his inner product is. We'll get 0, -2, +2, but that's still 0. So anything in the row space is orthogonal to the null space and vice versa. And I guess I should mention that this is the row space of matrix A and the corresponding null space of matrix A. Let's slide that up so you can see what's going on. Let me give you a minute to try the same thing with the column space of A and the null space of A transpose using the Euclidean inner product, also known as the dot product. All right, so we're back. And I inner producted the column space vectors with the null space vectors. And again, we see that we get 0. Showing again that the column space is orthogonal to the null space of the transpose of the matrix, which makes a whole lot of sense, because if we take and transpose the matrix, what was the column space of the original matrix will be the row space of the transpose matrix, and the row space. Let's write that down. So this would be equivalent to the row space of A transpose. And we know that the row space of a matrix is orthogonal to his null space. Okay. So we had a 3 by 3 A matrix above. If we find his rank is the dimension of the row space or column space, which in both cases we saw we had 2 basis vectors. The nullity of the A matrix is the size of the dimension of the null space, which would be 1. And just as a quick review, like we've seen, rank plus nullity equals number of columns. Now, just to show one other thing here, let's make up a non-trivial vector P in R3. And I just had my calculator randomly generate some numbers between -5 and 5. So it just randomly generated the vector for me, -1, 0, 4. What I want to do is express this P vector as a linear combination of the row space vector and the null space vector. So I'm trying to say that P vector is some constant multiple of the first row space vector plus some other constant multiple of the second row space vector plus some constant multiple of the null space vector, which the null space of the original matrix I did in red. So in other words, that's going to set up a system using our vectors here. So here were my row vectors, but set up in the system. -2, -1, 1 was the null space vector. And we're now going to augment that by the P vector that I want to make, which is, I'll do that in purple, -1, 0, 4. And let's RREF that matrix to see what the coefficients are, the coordinates are for the row space vectors and that null space vector to make this guy right here. So for my P vector here, if I RREF this matrix, I get 1, 0, 0, -1/2, 0, 1, 0, 3/4, and 0, 0, 1, 1. What that means is to make the vector -1, 0, 4, I need to do -1/2 times -2, 1, -3, plus 3/4 times the second row space vector of 0, 2, 2. Oh, I'm running out of space. Plus 1 times the null space vector, which was -2, -1, 1. And so that shows that I can make this P vector, who was anybody randomly chosen in R3, using somebody from the row space plus the null space. And we can do that for any general vector. If I were to pick A, B, C, I could hit him using linear combinations of the row space vectors plus the null space vector, which tells me that together the row space basis and the null space basis make a complete basis for the entire space. In other words, they complement each other. And we'll talk about that in the next video.